Hello, everyone. I'm Sarah Gutterman, CEO of Green Builder Media, and I'd like to welcome you to today's webinar titled Building Science Innovations for Net Zero Energy Homes, brought to you by NV Energy. This is part 2 in a Building Science webinar series. If you haven't heard part 1, don't fret. It's not necessary for you to have attended part 1 in order to understand the content in today's webinar, and we will send you the link to part 1 in a follow-up email after today's webinar in case you want to watch the recorded version. Why are we focusing so much attention on building science? Because it's paramount for building high-performance net zero energy homes. It's constantly evolving as building products, systems, and practices become more efficient, durable, and resilient. Today, Steve Easley, our guest presenter, will examine how changing energy codes will impact home performance, and he'll examine cost-effective, practical, building science-based solutions that building professionals can employ to meet these shifting code requirements and to build high-performance net zero energy homes. If you don't know who Steve Easley is, well, you should. He's an internationally recognized construction consultant specializing in solving building science-related problems and educating the building industry on building science topics and issues. He focuses on increasing quality of construction, sustainability, performance, and, importantly, reducing costly mistakes that lead to construction defects and all of those dreadful callbacks that none of us want. Now, before Steve shares his wisdom with us, I want to tell you about PowerShift by NV Energy. As we know, we can never save too much energy or money, and that's why NV Energy has introduced a program called PowerShift to help its residential and business customers conserve even more energy and save money on their power bills. PowerShift by NV Energy is also about providing their customers with excellent customer service. It's a one-stop shop to find energy-efficient products, services, and programs. PowerShift Energy Advisors are dedicated to working side by side with their business customers to discuss their needs and to find energy efficiency solutions that save money. So I encourage you during today's presentation to submit questions for Steve. In order to do that, just simply use the questions box on the right side of your screen. I will review those questions and pose them to Steve during the Q&A session at the end of his presentation. So please, again, submit questions throughout the course of the presentation, and I will keep track of those. So Steve, we're ready for you. Please take it away.
Well, thank you, Sarah, and good afternoon, everybody. Yeah, building science is kind of an important thing today. You know, when you think about how the codes have changed, we've seen at least a 30% improvement in energy efficiency in the last 3 code cycles. And as we increase the energy performance of buildings and homes in particular, that has an impact on durability and indoor quality and all these factors. But no reason to really fret too much about that. It's pretty simple solutions that can help get around some of the issues that we've seen happen in the field. And I'm going to address a lot of those today. But you look at, we have buildings in this country or homes in this country that are over 300 years old, and they're still doing just fine today because a lot of these structures weren't insulated. But as we add insulation, it reduces the drying potential. So sometimes people get the impression that, gosh, all this energy efficiency and insulation and making homes tighter is really creating problems. But that's not really the case at all. In fact, in my forensic work, I find that structures that are more airtight, better insulated, actually perform better, are more durable and long-lasting if we get the pieces put together right. Well, today I'm going to be focusing on the second half of this webinar, really dealing with some really cost-effective things that we can do, in particular dealing with air sealing, HVAC, and focusing on some of the things that I work with my clients about building zero-energy homes around the country. So first of all, let me share with you some resources that I participated in. These are free. This is a guide for designing energy-efficient building enclosures. And it's really geared towards giving you the details that are necessary to build really high-performance homes. And one of the challenges, as you may have noticed, if you're in some of the climate zones that require exterior insulation, and if you're building zero energy homes, you definitely should be considering exterior insulation, is how do you deal with those details around flashing, and how do you deal with the fact that, for example, if you're required to use wood sheeting and you put a non-permeable foam sheeting over that, how do you deal with that in terms of the moisture issues? And this book really addresses a lot of that. This was put together for the Canadian government, but it all relates very well to North America. And this is free. If you go to, I'll go back to the website here. If you go to www.fpinnovations.ca and click on Advanced Building Systems, or you can simply go to steveeasley.com and look under helpful resources, and you can download it there as well. So let's talk, first of all, last webinar we focused a lot on thermal improvement in terms of insulation choices, those types of things. I want to focus for a little bit here on how important air leakage is. We've all known for years that building tighter homes makes a lot of sense, but it's even more important today. I mean, even the codes in the least stringent climate zones are requiring 5 air changes per hour. And in the colder climate zones, 3 air changes per hour. And a lot of people are really struggling how to get there. And so we'll talk a little bit about that. If you look at this chart here, if you look at air changes per hour at 50 pascals on the left side, and then across the bottom is all the climate zones, you can pretty well see that in most climate zones, we're in that 6 to 12 air changes an hour, which is super, super leaky. And of course, when we have air leakage, that not only drives up energy costs, impacts comfort, but it also is a great way to move moisture in and out of wall systems, which can cause lots of problems. So when you look at the climate zones in the United States, pretty much in climate zones for the 2012 energy codes, it's climate zones 3 through 8. You have to do at least 3 air changes an hour. So a lot of people haven't quite got there yet. So we're going to talk about some practical ways to do that. Number one, I like to make these things as simple as possible. So what I advise my clients to do is install their ceiling drywall first after the exterior sheathing and cladding is on. And that way, if you install the ceiling drywall, you can test your blower door testing before ceiling and wall insulation. It's a lot easier to find those leaks, before insulation's in, than waiting till the building's done, and then you have to come back and figure out how you're going to air seal it. So just putting that lid on the building, that ceiling drywall, allows you to pressurize the building. So when you do your blower door test, it's really easy with a smoke generator or a smoke pencil to go around and find those leaks, and you're going to be much more likely and more economical to achieve that 3 air changes per hour or less. Now, the code, as I mentioned, requires in many climate zones 3 air changes an hour. Typically, in a zero net energy home, you're going to be looking at those air changes down between 1 to 2 air changes per hour. So it's even a little bit more stringent, obviously, than the code for obvious reasons. Thirdly, we want to test for leaks before the ceiling drywall is installed, because it's just more economical to seal those at that time. Now, if you look at the causes of air infiltration in buildings, we're all pretty familiar with the wind. Wind blows on one side of the building, creates a positive pressure, and on the other side a negative pressure, which pushes out the air you paid to heat and cool. We don't know about that. We may be somewhat familiar with the stack effect, because warm air is more buoyant than cold air, so it definitely has the tendency to rise, and that's why we tend to have higher humidity levels in the tops of buildings than we do at the bottom, and that's where we tend to have more moisture problems in attics, because as that more buoyant air is being forced out of the structure, it comes in contact with colder surfaces where it can condense. That's why non-vented attics today are popular, because it does help reduce some of those issues. And then finally, the one you might not be so aware of is how mechanical systems impact pressure differences. So those are the 3 ways that air moves in and out of buildings, and of course we want to minimize all those. So first of all, that starts with, if you can, avoid equipment with flues. If you're going to buy gas equipment, for example, you want to make sure it's a direct vent, so you have plastic pipes that are flues that run through the sidewalls, as opposed to going all the way up through the center of the structure like you see here, because these are holes that are very difficult to seal, and because of the stack effect, it's really easy for air to exfiltrate out of those locations. So for example, if you're a lot of clients that I have that do zero energy homes, they're using heat pumps, and heat pumps obviously don't have the flues, and the heat pumps also come in very small sizes. For gas equipment, it's tough to get small equipment for low load homes. And then of course we also have hybrid heat pumps or heat pump water heaters that obviously would not require a flue. And again, the purpose of this is to recognize the fact that flues are leaky. They tend to be holes that run up through the center of the house that are difficult to see it. So let's talk a little bit about the impact that duct leaks have on buildings. Let's just say we have a typical house, and I don't really care whether the air handlers, you know, in a basement or an attic or crawl space. We'll talk a little bit more about that later, getting those systems out of those spaces. But if we have no duct leaks, so say we have a 3-ton system, 400 CFM per ton, we have a 1,200 CFM blower motor. Let's say that's moving 1,200 cubic feet of air per minute through the return. We have no leaks. That means 1,200 CFM of air is coming out of the supply ducts. Everything's great, right? Building's under neutral pressure. But let's say, for example, like in a typical home, we have maybe 15 to 25% duct leakage. So that means, say, for example, here, if we have attic or crawl space, that means that supply ducts are located outside the building envelope. That means that that 300 CFM is going to be leaking into a crawl space or leaking into an attic. And that means that only 900 cubic feet of air per minute is coming out of the supply ducts. But the return air duct is pulling in 1,200. So where does that other 300 CFM come from? Well, it comes from outside the building envelope. And that puts the structure under negative pressure. So when you have air from the outside infiltrating in, that air has to have high moisture content, like in some parts of the country. That can lead to lots of problems. Also, it's important to recognize is if we have combustion products in our home, like fireplaces, for example, one of the easiest pathways for that air to come down that chimney. And so that could cause backdrafting in appliances. So, for example, if you try lighting your fireplace on Thanksgiving and you start noticing that you're getting a little bit of smoke coming back in the room, go turn off your furnace because it's probably putting a fair amount of negative pressure on your home due to ductwork. So sealing the ductwork eliminates these problems, gives us a healthier home because we have less opportunity for backdrafting, less opportunity for moisture to condense on the insides of the wall or build up, and also it's a lot more energy efficient. Let's say, for example, a common mistake that I see happening, for example, here you look at a typical fireplace, and you'll notice that we also have a return air duct chase in that same cavity. So when drywall is put in around this, that means if there's any leaks in that duct, return air duct, that's going to put a negative pressure on that area. And if the flue next to it by that fireplace happens to be leaky, which they almost always are, you could actually pull these kind of toxic gases back into the return air duct system. So what I'm saying here is you never want to put return air ducts in the same cavity with combustion appliances, because that's kind of a dangerous thing to do, and it's not very energy efficient. So you want to seal those ducts and also make sure they're not located in the same cavity. So what happens if your home happens to have a lot of return air duct leaks? Well, let's say our return air ducts are in attics, like in many homes they are, particularly new homes since we do slab construction. We'll say that we have the opposite effect happen. So let's say we have 300 CFM of duct leaks that are happening on the return air side. Return air ducts suck air, so that means it's going to be under negative pressure like in this attic. So that means if we have 1,200 CFM coming out of the supply ducts and only 900 CFM coming through the return air register, that means that other 300 CFM is coming out of the attic. So basically what you're doing is that you're drawing 300 cubic feet of air per minute of 110 to 140 degree attic air into that system. So now in the cooling season, your system has to work really hard to overcome 110 degree or 140 degree air going through the air conditioning system as opposed to the air inside your home, which might be 80 or 85. So it's really important from an energy efficiency perspective that we seal those ducts. Now, if you want to see some examples of what can happen, this is an example of a contractor who decided that he would use a return air duct or a duct from the outside to be brought into the return air duct of his home. So, for example, it's common that if people want to put fresh air into their system, they might just simply run a duct from the outside and run it into the return air duct at home. So when the furnace runs, it pulls in that fresh air from the outside. Sounds like a good idea, right? Well, it's not really, because it's uncontrolled ventilation. It only works when your system is operating, and also it can create problems like this. In this case, the home had high humidity, and the home obviously was under a positive pressure caused from the excessive supply duct leaks, which is what a duct going into the return air side would do from the outside. So as that home was under a positive pressure, it drove that warm, moist air out through every crack and gap in the home. And of course, as you're probably aware of, the joints between your sheathing and your framing are pretty leaky. So as that warm, moist air in that pressurized environment being forced out through all the cracks and gaps in the building envelope, it slowly dampened those surfaces, and you can see the mold growing in the upper corner here. So my message is this. Sealing your ductwork is really important, not only from an energy efficiency perspective, but also from the perspective of driving moisture in places that we don't want to happen. So it's really important, number one, to keep ducts in conditioned space, and I'll show some examples of that in a bit. But also, make sure that the ducts are well sealed so that we don't have these moisture drivers. Now here's an example in a colder climate where you can see mold building up inside the walls, and if you look carefully there, you'll see an outlet. So if you ever put your hand over an outlet, you might notice a draft. Well, in this case, the home was under a slight positive pressure, and so what happened was the air escaped around the outlet, slowly dampened the surface of the sheathing, the point where the surface relative humidity got above 70%. And the reason why that number is an important one is because when the surface relative humidity of building materials gets above 70%, those are the conditions which mold start growing on building materials. So again, this is a classic case of where a leaky home is actually creating more problems than one that was tighter. So the air is always warmer and wetter than the air is driven to. So what happens is that moisture builds up, and then of course it doesn't have the capacity to dry very well, and we see conditions like this. Give you an example of this. If we look at this chart here, we'll say that we have air inside the home that's at 19% relative humidity, and the air is at 70 degrees. And as that air exfiltrates out through the wall cavity, let's say it's cooled down to 35 degrees. Look what happens to the relative humidity. It goes up to 70%, and I didn't do anything to that air but change its temperature. So having a leaky building envelope, having ductwork that's leaky really contributes to not only poor energy efficiency and higher bills, but also potentially mold and moisture-related problems. And in fact, when you look at a picture like this, this is not mold growing on that insulation. This is actually dirt. And so it's so important that when we have a good air barrier system, we make sure it's well sealed and our house is tight, because everywhere that you see the dirt here is where? You look carefully at this slide, you'll see that everywhere the dirt is at is where you have a leak around wiring or outlets or switches. And in this case, there's a lead-in brace that goes on the exterior core of this building, and it's probably not quite flush with the drywall, so it makes it really easy for air to infiltrate in. So it's not that fiberglass is a bad insulation, it's just not that it's a good air barrier. So one of the most cost-effective things you can do is do a good job of air sealing the home as well as sealing the ductwork. Here's a good example of a home that's under negative pressure. You see the dirt build up around the carpet edges at the trim. This is on an exterior wall. If you take another look at this, you can see the dirt building up in the carpet. That's because around the exterior walls, those plates are very, very leaky. And so that's why we always want to take the extra step of caulking those plates to the subfloor and also putting a good air barrier system around the exterior envelope, doing this air sealing, and again, doing this before you put the drywall on, before you put the insulation in, measuring before you put the insulation in. It's going to ensure that you're going to have much greater success and not end up with something that looks like this. And one of the most common problems that I see in new construction is dealing with can lights. Even though these can lights meet ASTM E283 specifications, they still do leak. And unfortunately, can lights are popular because they're inexpensive, but they leak and they create holes in the building envelope. And so when you look at all these holes, every one of them adds up. We see oftentimes homes can have, upwards of 15 can lights in. And even when the lights are off, you can see here, for example, that air infiltrating in on a hot day. So it's not just the winter months that we care about. Okay? So a lot of times people think that if we just blow insulation over the top of our attic, we've done a good job of air sealing. But what I want to point out next is going to fascinate you, I think. This is a 1970s vintage house, about 3,500 square feet. about 1,500 square feet of attic space. The blower door testing on this house was 4,460 cubic feet of air per minute. That was before the air sealing. And then if you look here carefully, you can see where the wall plates are at, the can lights. Most people aren't aware of the fact that where these interior walls, they leak like crazy too. We tend to be focused on exterior walls, but interior walls can be equally as leaky. And that displaces the air you paid to heat and cool. So this is what kind of happens on the interior walls. You have air that infiltrates in at the base of the walls, comes up into the attic, and then escapes around that. So it basically is like a small chimney, just basically pulling the conditioned air out of your home up into the attic. Well, just retrofitting this house, just air sealing the attic around the plates, around light fixtures, any penetrations, plumbing walls, these types of things like this, the air infiltration rate went from 4460, get this, to 2180. Cut the air infiltration rate of the structure in half just by air sealing the attic. So it's really not as difficult to get to some of these numbers and lower than code numbers than you might think if you just pay close attention to detail. So number one, make sure that when we just don't rely upon insulation to do air sealing, because it just does not work. You've got to pay close attention to all these details. Now, another product that I really like a lot, and there are a couple different manufacturers of these are these flush mount LED can lights. So they're like canvas lights. If you look carefully at this diagram, you can see that these things are only about 5/8 or 3/4 of an inch in depth. So they actually flush mount, and so that they can just have a standard, electrical box above it, which makes it really easy to air seal with simple caulk or even spray foam for that matter, and it gives you great light output. We're seeing some of these fixtures put out well over 100 lumens at 2700K, which is very warm, nice light. They even have LED technologies now that have orange LEDs in them, so as you start to dim them down, they even replicate incandescent lights all the way through their dimming spectrum. So you really don't see any penalty at all for using LED lights, and it's a great opportunity to reduce air exfiltration and infiltration at these locations, and even get better quality light. So in summary here, well, I think it makes sense if you're looking for ways to economically air seal your building envelopes and cut your air infiltration rates in half, is to simply air seal all the way around the perimeter, like you see here, air seal all of your interior walls as well as exterior walls, and then air seal over any penetrations, electrical boxes, things of this nature. Obviously, always making sure to follow the appropriate fire protection system. Some my builder clients are even doing things like this, where they'll put down a few inches of spray foam along the entire attic. I would probably consider this maybe good, better, and best. Now, one of the things that's really important to do too is to use raised steel trusses. As you can see here, this is just a standard scissors truss, but there's not much space for the insulation here. So how that manifests itself in the real world, if you happen to be in a climate where you have high humidity, or where maybe even you have colder conditions, you could actually get mold to grow in those locations, because the insulation is compressed so much it doesn't have the ability to insulate very well. So what happens here, if you look at this picture, you can see there's no mold growing on the interior wall, but at the corner of the exterior wall where it intersects the ceiling, you can see lots of mold growing. That's because the surface relative humidity there is above that 70%, because it's colder, because there's more heat loss. So having a raised steel truss sort of prevents some of these types of things like you see here, and even foaming around the edges is another step forward to reducing that. So raised steel trusses really make a lot of sense, not only in terms of making your home more energy efficient, but also make it a little more durable and long-lasting. Now, the Building America program is a great resource for all sorts of information. If you just Google buildingamerica.gov, you can get all kinds of great studies, measure guidelines that really walk through and help you do all sorts of energy-efficient measures in your home. This, for example, is one on air sealing for retrofit technologies. Other areas: avoid all drop ceilings. These drop ceilings are just a bad idea. In the real world, it seems to make sense, because the framer comes in, they put up these soffits, and then the drywaller comes in and drywalls over it, but they end up being very, very leaky. So putting a simple step of putting the drywall first creates this continuous air barrier, eliminates that drop ceiling, and reduces a lot of the issues associated with that. Also, areas that are really difficult to insulate probably makes a lot more sense to use spray foam like we see in cathedral ceilings sometimes. Here, these do not need to be vented because the surface temperature of the roof deck never reaches its dew point because of the thickness of the insulation. So we don't have to be afraid about doing non-vented attics. For example, here's a good example of that. You might be asking yourself, well, how do non-vented attics work? The purpose of venting attics is to get rid of the moisture. Well, when you look at a traditional attic where the insulation is at the ceiling line, air exfiltrates around that insulation, and then the roof deck above it could very well be cold, even in very warm, dry climates. So when that moisture comes in contact with the bottom of the roof deck, it can be absorbed by that, create lots of problems. How a non-vented attic works is that we take that insulation that was on the ceiling line and we move it up to the bottom of the roof deck. And because of the fact now that roof deck is insulated, it's just like the ceiling in your home. It never gets close to its dew point, and so therefore that's how non-vented attics work. Now, in some climates, of course, you have to be careful and you have to make sure that you follow up with the appropriate vapor retarders. So, for example, in the 2015 IRC, the climate zones 5, 6, 7, and 8 require that if you have any air permeable insulation, shall be a Class 2 vapor retardant. So closed-cell spray foam, for example, greater than 2 inches would qualify for that. But what if you're using open-cell foam? Well, in those climate zones, because open-cell foam is vapor open, it allows moisture vapor to pass through it, you would have to cover that with some type of a Class 2 vapor retarder coating or covering in direct contact with the underside of the insulation. So check your local codes on that. But in general, non-vented attics can make a lot of sense. Also, if you happen to have your ductwork up in the attic, that creates a conditioned attic space, and therefore you're not losing all that energy that's lost through typical leaks in the ductwork, and you're certainly not going to have those tremendous attic heat gain issues that are associated in your cooling climates. Also, there's other technologies around there for air sealing that seal at all these plate lines around the perimeter that reduce that. So there's a variety of different companies that are making products like this that can be helpful in terms of air sealing. Don't forget, if you are using crawl spaces, that they can be very leaky too. So crawl spaces can be just as leaky as attics. So that's why homes constructed on slab floors are typically tighter. So if you have basements or crawl spaces, it's really important that you air seal those as well. Even slab floors, you may think that there's no need to air seal those. This is a project that I looked at in the Chicago area where they did not seal underneath the slabs. They had a little bit of an issue with water running underneath the slabs, and so every time that the HVAC system turned on, people would smell mold in these duplexes. And the reason is that the ductwork had quite a bit of duct leakage, so it put the home under negative pressure. So guess what? Every time that the HVAC system turned on, it would pull that mold-infested air from underneath the gravel in the slab through locations like this around tubs and penetrations in the slab and create the problem that the people experienced with indoor air quality. So the solution was simply to come back and air seal these locations and then seal the ductwork. So now you're starting to see why building science, looking at everything in terms of the whole system, the whole house, is really, really important. Sometimes you wouldn't think to do this, but it becomes a very expensive callback to have to come back and tear out drywall to seal that up later. So number one, good water management on the outside could have prevented this. Number two, air sealing at penetrations in the slab. And number three, making sure that the ductwork was well sealed and didn't create any pressure differences that caused the home to be under negative pressure, and thus the slab area to be under negative pressure and draw that area into the home. Other areas where it's important to pay attention to, you might think that if you have some insulation on the wall here and you come over this with drywall, that that's going to be a good air barrier system, but actually it's not. So a better approach would be to drywall the inside of that space, caulk and seal that, because there's a lot of area that communicates to the outdoors. So when we talk about a holistic integrated product design and delivery approach, it means thinking these things through before the process than just getting the drywall up, doing a blower door test and saying, oh gee, what do I do now? All right, so let's talk about some HVAC solutions and in particular things that we can do to make these systems work better. As you can see here, this is a HVAC system that was installed between floors of a two-story structure, and they just didn't have enough room for the ductwork. So when the installers got there, they just crammed it in any way that they could. This is not thinking ahead. This is not an integrated project design and delivery where you map things out beforehand to make sure that these types of things do not happen. So some performance characteristics and problems that I see happening on a day-to-day basis, obviously duct leakage, that affects both heating and cooling. Duct conduction, not having an adequate amount of insulation or ductwork affects both heating and cooling. The refrigerant charge is almost always wrong, at least 6 out of 10 times. That affects mostly cooling. Low airflow, mostly cooling. In other words, having restrictions like you just saw on the last slide reduces airflow. Oversizing, there's a real tendency in the industry to oversize HVAC systems because people don't want to call back. That means the unit short cycles more. What happens in some climates where the system doesn't run long enough to dehumidify the air. Remember, the homes are tighter, so the humidity level is going to be higher. So it meets its sensible load really quickly, but then doesn't run long enough to dehumidify. So even in hot, dry climates, this can be an issue. Room-to-room airflows, mostly heating and cooling. In other words, not having balanced airflow throughout the structure leads to stratification and some rooms being too hot, some rooms being too cold. Obviously, equipment efficiency and equipment defects. So if you look at attics, obviously they're leaky and ducts are almost poorly insulated. And then they're hot. Attics get upwards of 140 degrees. So if we have ductwork up in that attic and that ductwork happens to be leaking, it's going to suck that hot air into the ductwork system and really drive up your cooling costs. So what everybody's trying to do is, from a zero energy home perspective, is get the ductwork out of non-conditioned spaces. Okay? So traditionally what happens when we put our ductwork in an attic, they leak and they're poorly insulated. I mean, even in today's code, we require most climate zones R8 insulation. And so let me run through an example of what that really does for you. If you look at a typical house, the amount of ductwork compared to the surface area of the floor area is about 40%, believe it or not. Can you imagine that? 40%? Certainly 25 to 40 would be kind of a range that I would say. And if you go through and you do the math, and if you have ductwork that's insulated to like a typical older home to R2, that would be the equivalent, just because of the surface area of the ductwork and the conduction losses associated with that surface area of the ductwork, that would be the equivalent of almost 2.5 tons of air conditioning load. Now, if we add and go to R8 insulation of the duct, that reduces that to about 0.13 tons of refrigeration or air conditioning. Now, a ton of air conditioning is 12,000 BTUs per hour, and that relates to the amount of energy it takes to melt 1 ton of ice in days of old. So reducing your loads by adding appropriate duct insulation is helpful, but wouldn't it make a lot more sense just to put that ductwork in conditioned space so we're not so concerned about those types of losses? Other approaches is you can use R8 insulation, and then you can bury the ducts. That would be great, R20 or more. Now, another great publication from the Building America program to the Department of Energy is this measure guideline that tells us and teaches us the value and how to do buried or encapsulated ducts below floor line or above attic spaces, for example. And that combination of different ways you could do that. You can use spray foam. You can bury the ducts deep into insulation. Lots of different approaches. So even if you're not moving ductwork to conditioned spaces, you can still solve some of these problems if you're building traditional homes. Just a matter of paying close attention to those types of detail. So ducts in conditioned space obviously eliminate the issues of attic heat gain. They eliminate air leakage to the outside and resulting in pressure imbalances. They have the ability to downsize HVAC equipment, sometimes dramatically. And there are several approaches to how we might go about putting ducts in conditioned spaces. One, for example, you could do, you could simply lower the ceilings in hallways and put your ductwork in the hallways instead of up in the attic. One, we could do a non-vented attic like you see all the way here on the left, where we basically use some type of foam insulation at the tops of the attic so that we basically create that as conditioned space. The second is a drop ceiling like I just showed you. The third is where we can put the ductwork between floors. And the fourth method is where we basically create a plenum that's up in the attic, like say with a scissors truss or a specific type box truss, where we can put that equipment, still have serviceability, but at the same time, and it doesn't impact interior space. So that's really a simple overview of how we might go about some of these things, and I'll show you some more detail here in a moment. But as I mentioned earlier, these non-vented attics or unvented attics can be a very effective place to put HVAC equipment, because once we move the insulation to the bottom of the roof deck, that essentially becomes semi-conditioned space. And so that allows us to avoid the penalties that you might have from having return and supply ducts up in 110 or 140 degree attic. And don't forget, the penalty is still there in the winter months as well. So it's not just the cooling climates that can benefit from this. It's all climates. So here's a kind of a closer view of how we might do a drop ceiling. What we've done in some of the homes that I've consulted on is that the builders have essentially, they do 9-foot ceilings anyway, or maybe 10-foot ceilings, even in one-story buildings, 9-foot and 2-story buildings. And then they'll drop the ceiling down to 7.5 feet in the hallway. So you really don't notice the lower ceiling as much as you would if you had an 8-foot ceiling and then drop the interior hallway to 7 foot. But these are really practical ways that you can employ today that doesn't have to cost a lot of money. Another option that's not terribly expensive are these plenum truss designs. And so, for example, one here at the top is kind of basically that whole box out area is a space for the plenum, and you drywall the inside of that space, air seal that so it doesn't communicate with the attic, and you've got a lot of space for equipment. The second one is more like a scissors truss design, and that could be integrated in places where you want to have a sloping ceiling, and in those areas adjacent to it, you simply use that same space to put your HVAC equipment in. In the real world, it looks sort of something like this. You can kind of see the actual photograph. You can see that the space for the plenum area is drywalled around the perimeter of the trusses. And then if you look at the diagram at the top, you can see that the thermal barrier is up over the top of all that. And so therefore, your ductwork is isolated, from the unconditioned space. Other options, we can run ductwork in conditions like this, where we drop ceilings. This is an actual real-world pictures of some of that type of activity. Here's an actual plenum truss. You can see that the top of this was covered with radiant barrier sheeting product, and then it'd be insulated over the top. And so this was kind of a clever idea because, as you're probably aware, radiant barriers, they do a good job of reflecting radiant energy. And you may be asking yourself, well, wait a minute, how does this work upside down? Well, shiny surfaces can't give off the energy very well. Not only are they reflective, but they have very poor emissivity. So that means the energy from the sun doesn't strike a roof deck, you irradiate it in the scissors truss area. The shiny surface of this foil sheathing couldn't give off its energy very well, so that would basically equate to about a 30-degree cooler space. And then, of course, you would insulate over the top of that to further provide thermal integrity and protection. But it's really just a very simple thing that you can do to reduce, the losses associated with ducts in conditioned spaces. Also, plenums and soffits, these need to be thought out in advance, but much easier to do that than it is to pay the penalties of putting ductwork in attics. And some of these can be attractive and be part of the architectural appeal of structures. So let's look at some of the other things that we see that kind of go wrong on a day-to-day basis. The Proctor Engineering Group has done a lot of studies on this, as well as Stolzenhoff, and they did some studies to kind of really figure out what the state of the industry was. And when you're looking at failure to use recommended evacuation methods for refrigerant lines, 72%, failure to confirm proper airflow. In other words, if you're trying to cool air or heat air, it's important that you get the right amount of airflow across the heat exchanger or the air handler in order to deliver the comfort. And they found that 72% of the time, these systems were really lacking in that area. And then finally, the failure to use the recommended refrigerant charging method was about 74%. In fact, one study that John Proctor had done showing that 62% of the time, air conditioning systems did not have the appropriate refrigerant charge, which is really impactful in terms of the overall performance. And then when we see, workers make mistakes like this, where the ductwork is crushed or sealed, that creates issues. Not having proper design. We talked about pressure differences a little earlier. If you look at here, for example, this is a typical house where most homes don't have return air ducts in bedrooms, and so oftentimes they rely upon cutting off the door at the bottom. So what happens is if you don't have any type of mechanism for air to flow from these rooms with doors back to the central return, you can have one part of the structure under negative pressure, another part under positive pressure. You're not going to get good airflow. You're not going to get good comfort. Certainly not going to get good energy efficiency. So what would you have to do? How much would you have to cut off that door? Well, if you had, let's just say, even a 30-inch door, and you had a need, let's say a typical bedroom might require 150 to 200 CFM, and if you look at this chart, the clearance from the floor to from the door to the top of the carpet would have to be 3 inches. So that means for a typical, 12 by 12 bedroom, you have to basically cut the door 3 inches above the floor to get adequate airflow. So what are the solutions there? Well, we can do transfer grills. We can do jump ducts like you see here. This is just a duct that goes from the bedroom into the hallway where it can communicate freely with the return air duct for the system. And it's economical, and it really helps increase the overall performance of the system. We could also do transfer grills. We simply just cut a hole between the two and allow for air equalization. You have to be careful about how you size these, but it's another way to make that work. Or you can run a dedicated return air duct for each of the bedrooms. Speaking of return air ducts and filter grills, some of the issues that we see on a day-to-day basis is that these are not adequately sized. You do not have the adequate airflow, in particular if they're filter grills. In other words, if you have a furnace filter that's basically behind this, and you're trying to move an adequate amount of airflow, you're going to be in trouble. So making sure that these are designed appropriately and they're not restrictive is going to make sure that you're getting airflow. And these are things that are totally, oftentimes not even thought about. And so, for example, when you look at more of a high performance, like this is a grill that's made by a company by Shoemaker, you'll notice if you look carefully that this has got, really well engineered, really well designed, and you have its egg crate design is very different than your typical louvered stamped metal design. So you're going to get way more airflow through a product like this than you would a product like this. And these are often not even thought about. So having a well-designed and engineered HVAC system up front is really important to getting the delivered performance. So oftentimes homes look great on paper, but in the real world they just don't perform well for a lot of these reasons. For example, here, look at the impact of this fold and this duct is going to have on airflow. And again, you can't condition air unless you can move it across a heat exchanger. So making sure that you avoid all these kinked ducts and areas where you're folding ducts over structural members. This is a 12-inch diameter duct. How much air could possibly move through that? And these are the things that we see in the field every day, and it's because we don't think through the designs up front. And that's really what we mean about integrated design and project delivery, is making sure that we have a pathway for all the ductwork and making sure we have inspection protocols to make sure that these things don't happen. A lot harder to fix these in the field. Here's a great example. We got a 12-inch joist space in a 2-story house. We got a 10-inch diameter duct, which is being compressed by a 4-inch soil line. So how much air is possibly going to come out of that register to the left? So it's going to suffer from some significant comfort issues. So give you an example of how all this adds up. This is some calculations that Proctor Engineering did, John Proctor. And if you have a 200-foot straight piece of pipe, and then you take that same piece of ductwork and you bend it in configuration like this, what do you think it's equivalent like this in terms of friction loss? Do you think it's 100? You might be surprised. Just this small bend like this created a length from 200 to 330 feet in terms of friction loss. So making sure that you have adequate airflow is really important. In fact, some of the studies have shown that we see, this is a 62-unit study that Chitwood did. You're looking at some of these homes were down as low as 150 CFM per ton, all the way up to something that was close to being right at 400. So getting the airflow across the coil is really, really important. And the only way you know that is you measure. And these are the types of things that prevent that airflow. When plumber always wins. And we see these types of things over and over again. There's just no way you're going to get the desired comfort or efficiency out of the system with regards to installations like this. So what do we mean by good strategies? Well, they have CAD programs today that can allow us to do this layout with the specific framing of an individual house. So it just needs to be done up front. Really easy to do this. It's just a matter of taking the time to make sure that these systems can and do perform. Otherwise, you're doing lots of expensive repairs and so forth in the field after the fact. It gets expensive. In fact, like here, for example, this is quite a bit more money to take into account this beam. Okay. Here, for example, we see that we've got building cavities that are used for duct spaces. If you look at the top of the slide, you can see just a stamped piece of the sheet metal that's a register it goes to, and then there's a hole cut in the floor. Building cavities by code can no longer be used for ductwork. Now, if you'll notice here, you can see the copper piping and the soil line is right in the middle of the ductwork, because that cavity and that stud wall now is a supply or a return air duct. We also never want to put ducts on exterior walls. The temperature differences are far greater than just the ambient temperature differences in the room. So we don't want to put ductwork on exterior walls. They're difficult to insulate and difficult to seal, and create conditions where you get mold growing in the walls because of the duct leakage. Okay? You never want to do things like put soil lines inside of our ductwork. So even return air ductworks, you can't use building cavities. So if you look at this, you can see that all the black marks around the insulation, that's a pretty significant duct leakage. So again, this is outside the conditioned space. It's in the garage. It's not air sealed, and it really detracts from the overall performance. We see these systems operate at 50% or less than their intended capacity, and that's why we have to do things like put multiple units in homes, because we don't pay close attention to building enclosure, we don't pay close attention to design, and we don't pay close attention to duct sealing and measure. You don't know unless you measure. Okay? And air sealing methods are important as well. The reason why we don't like to use rubber-based duct tapes anymore is because the adhesive dries out. This home's not even finished yet, the duct tape's falling off. So we want to use appropriate methods for air sealing. Maybe work great for your Cadillac, but not so good for ductwork. Also, it's important that when we do the air sealing, we make sure that we put our test metrics so that we're measuring when it's done as well as at rough end. So in other words, here, this might appear that this home has less duct leakage than it would when it's finished, but because they put the air seal over the perimeter of the inside where the duct interfaces the boot. But if you pull that off, you can see that that's not air sealed. You can see a lot of air leaks around the perimeter of this boot. And so this home may look good in terms of its testing, but unless the testing is done right by qualified people who follow ResNet protocols, chances are you're not going to see the performance you're hoping for. Okay? So air sealing is important, continuous air sealing. Make sure that we get good proper seals. And that's all the components, whether it be flex duct or whether it be metal duct, making sure that all these joints and connections are well sealed. And these are the type of things that add up quickly in a home that really reduce its overall energy performance. So anytime you see black marks on the insulation, pretty good idea that that ductwork is not performing well. Okay? So it's really simple. Use a UL 181B FX type tape for if you're using flex duct. So you pull the liner over, you put the tape around that, and you put a drawband, and you pull the insulation over the top of that, put a drawband around that. It's a simple, cheap, inexpensive way to make sure that you're air sealed. There's typically 3 types of duct tapes that we like to see used, depending upon the application. Here's this clear, looks like packing tape, but that really has an acrylic adhesive that will squirt pretty well. Here we have a butyl-based, foil-based material, and then we have an acrylic-based foil. All these work in slightly different applications, but these are all very good tapes to consider using for air sealing. So it looks like I'm out of time, but I would like to take some time to answer some questions.
Great. Thank you so much, Steve. I have a couple of questions from attendees, and I encourage everyone to use the question box on the right-hand side of your screen to send me some more questions. The first low-hanging fruit question from Hector is if we will make this PowerPoint available, and I just want to make sure everyone knows that we'll make the full presentation available. We'll send you a follow-up email with a link to the recorded and archived version of this presentation soon, within the next few days, so please keep an eye open for that. Now, moving on to some more challenging questions, Steve. I have a few here. The first one is from Stacy, and Stacy asks, can you tell us what the major differences are between the 2012 and the 2015 code relative to kind of building science applications and net zero energy requirements?
You know, the difference between the 2 codes is really, really very small with regards to the difference in performance. Basically, in my opinion, the 2015 code, they just cleaned up some of the things that was in the 2012 code. So there's, and this, please keep in mind, this can vary jurisdiction by jurisdiction. And let me explain that a little bit. First of all, when the IECC or the ICC sets up these codes, they put these codes up for adoption. And this is their 3-year cycle. However, the states have a choice. They can adopt that as a statewide code. They can adopt it as a statewide code with their own specific amendments, or they don't have to adopt it at all, and they can leave it up to their own individual counties and cities to adopt that version of the code. That's why codes are so complicated. So, for example, if a state adopts a statewide code, they might say, gosh, we like all this, but we don't really think this 3 air changes an hour thing is a good idea. So we're going to adopt the 2015 code to say, well, we're going to go with 5 air changes an hour instead of 3. So you've got to really look at your own individual codes. Likewise, a state can adopt a code, and then individual cities or counties, they can adopt a stricter version of that code. So that happens in some cases. Now, the Home Rule Doctrine typically states that if you adopt a statewide code, even with amendments, no other jurisdiction within that state can go less than that code. They only can go stricter. And then, of course, you have the option of each individual, if there is no statewide code adopted, anybody can kind of do whatever they want if they want to adopt a code. So that's why codes are complicated. So I want to caution you, make sure you look at the codes in your specific area. But in general, what the 2015 did over the 2012, there's some issues with ventilation. There are some issues with backdrafting or combustion appliance safety testing, because when you start getting the home down to 3 air changes an hour, 5 air changes per hour, you can have basically a draft hood, like a range hood, backdraft your fireplace. So there was some language put in there to sort of help people understand the importance of doing combustion appliance testing. But that in a nutshell is what I would recommend is basically check your own local area, because it literally does vary state by state and even potentially city by city or county by county.
Thanks, Steve. And given that, we understand that codes may vary in different jurisdictions, counties, and states, but on a high level, what do you anticipate for the 2018 code, again, relative to enhanced building science requirements? Yeah, let's start there. I got a second part of this question. But...
Oh, sure, sorry.
Nope, go ahead,
okay.
Please.
Well, first, all right, so I think the big changes that you're going to see in the codes going forward are really going to be qualitative. I mean, when we're looking at, and some climate zones are 13 plus 5, some climate zones are 13 plus 10 or are 20 plus 5. The codes are definitely moving towards exterior insulation for good reason because of a lot of the thermal bridging things that I pointed out in the first webinar. So I think another area that you're going to see changes being made is going to be in the area of just making sure, like, you follow ResNet, like grade 1 installation install. So maybe you'll see some changes around windows. Right now, in the hotter climate, or in the cooler climates, like climate zones 5 and above, there's not a lot of guidance towards or requirements towards using low solar heat gain coefficient glass, which, if you look at climate zones 5, for example, so a lot of Nevada's in, you still have quite a bit of air conditioning load in those climates. But yet, there's not really very many strict requirements around using low solar heat gain coefficient glass. So I think you'll see some change in that area. But I'll tell you a great, if you go to NREL or you can also, they typically are pretty good about having these little PowerPoint presentations that say what are the changes between the different levels of code. So if you just Google changes from the 2012 to the 2015, or expected changes from the 2015 to 2018, you'll see some pretty good PowerPoint presentations that typically these guys have generated at NREL and Pacific Northwest Laboratories in particular. They're DOE labs. They've done some good work with regards to telling us the differences between the two codes. I might even have one handy here that maybe. No, I don't. I thought I did. Go back. And the second part of that question?
Yeah, the second part of that question is, when do you think net zero energy homes will actually be mandated in code? And that's kind of a two-part question, one for California, and then the second part is everywhere beyond California.
It's when we do a good enough job of educating consumers. Builders will build anything that consumers want. They're aggregators of products and materials to build homes. And the biggest problem that I see right now is just consumer demand. California, for example, they have a mandate that homes be zero net energy by 2020. The government wants all commercial federal buildings to be zero energy by 2030. So I think part of it's going to be regulation. Hopefully part of it will be tax incentives. Hopefully we'll start to see some tax incentives in terms of property tax relief to where people who buy a zero energy home get a break on their property taxes. Every county in the country could do that tomorrow. That would be a great opportunity to drive zero energy homes. And keep in mind that when we start looking at what's going to happen with electric vehicles in the next 10 years, that's going to increase electric cars probably by easily a third. So we're going to be needing to have zero energy homes just to offset this demand for electric cars, which I see to be tremendous over the next 10 years. For example, Mercedes just announced that they're going to come out with an all-electric vehicle 2020. Chevrolet is going to come out with their new Bolt, which is an all-electric SUV in the next 2 years. I mean, we're starting to see the success of Tesla, obviously. So I think that it's going to force, a different way of thinking with regards to incentives. So I think that to answer your question specifically, I would say that we'll probably start to see some significant changes in the next 3 to 4 years. But as far as a government mandate, boy, I think that's probably be at least 2025 would be my guess. And not a mandate, but like a code requirement.
Yeah. Okay, thank you. I've got two more questions, one from Allison and one from Brett, and then I think we'll be out of time. Allison asks, what is the size home at which you would move from ductless mini splits to an all-electric air or air heat pump for home, specifically, she asks, in Southern California?
Okay, well, first of all, when you look at the ductless mini split systems, they tend to be better geared for really open floor plans, typically smaller structures. Like, for example, we start looking at 1,000, maybe 1,200 square feet. I think you're probably starting to look at a time when the economics for multiple mini splits starts to diminish a bit. But keep in mind that the goal behind doing zero energy homes is to make the building enclosure as well insulated as possible so your loads are less consequential. So it's really more of an issue about comfort and air distribution and aesthetics because you can get really good performance out of a split system if it's installed and engineered correctly. So I would say that, I guess if I had to give you a number, I would say probably when you start getting above 1,000 square feet, that's when, and again, layout has so much to do with this. I mean, many splits in themselves to more larger rooms, open spaces that, you can get by with just one, evaporator coil that, can move enough air. It's a sizing issue.
Thanks, Steve. And I've got one last question from Brett. And Brett asks, how would you recommend sealing off existing fireplaces with inserts being installed?
Boy, that's a tough question. Boy, the Department of Energy and other people have been thinking about this for years. Obviously, if you have an insert, that's kind of a good first start because they typically have a little tighter damper system and so forth. I guess I would say where that insert interfaces with the old fireplace using a good fire-resistive insulating caulking material that you can air seal, do a blower door test, and make sure that you do the best job you can of air sealing, being cognizant of the fact that using a material that would be approved for a fire-resistant application. Obviously, if you can, in new construction or even in retrofit, if you can use direct vent equipment or no fireplaces at all, that's obviously the better choice. But if you are going to put a fireplace in, direct vent combustion seal equipment is a better way to go, simply because it's a little tighter. But they are holes in the wall. There's no doubt about that.
Wonderful. Steve, thank you so much for your time and for sharing your knowledge with us today. I also want to thank our audience for attending and asking some great questions. And last but certainly not least, thank you to NV Energy for their generous sponsorship. To everyone, please keep your eyes open for our next webinar, which will occur on December 14th at 2 Eastern, with Energy Code expert Bill Fay, who will provide insights and some interesting scuttlebutt from the 2018 code meetings that just took place recently in Kansas City, and he'll talk a little bit more about what we can all expect in the next round of code adoption and implementation. So please go ahead and mark it down on your calendars. Again, that's December 14th at 2 p.m. Eastern. So again, Steve, thank you. Thank you, NV Energy, and we hope to see you all again soon on the next webinar. Take care.